In the world of computer networking, everything really boils down to identity. Devices are constantly asking two fundamental yet totally opposite questions. Where are you and who am I? Today we're going to dive into the clever networking tricks that were invented to answer those questions. Proxy ARP and its now obsolete counterpart, Reverse ARP.
All right, so let me paint a picture for you. Your computer has an IP address for another device, and it just assumes, hey, this guy must be on my local network, a direct neighbor. But what happens when that device is actually on a completely different network, maybe miles away, with a router sitting right in the middle? How does your message possibly find its way there?
Well, the answer is a really slick technique called Proxy ARP. It's sometimes nicknamed the helpful imposter, and you're about to see exactly why. It's a trick that routers use to make communication feel totally seamless, even when it's happening across totally separate networks.
So here's the absolute key to understanding this. Proxy ARP is when a router basically steps in and says, don't worry, I'll handle that. When one of your devices sends out a request asking for the physical MAC address of another machine, and that machine isn't actually local, the router jumps in, intercepts that request, and answers for the remote device.
A great way to think about it is like a super helpful hotel concierge. Let's say you want to send a package to a desk, but you find out they've already moved to a different hotel. Now, instead of just sending you away, a good concierge would say, hey, just give it to me. I'll make sure it gets to them. In our scenario, the router is that concierge, acting as a trusted middleman.
Okay, so let's break this down into 4 simple steps. It all starts when host A broadcasts an ARP request, basically shouting, hey everyone, who has this IP address? The router sees this, and because it's a router, it knows that the IP address is on another network it can reach. And here's the trick. The router replies with its own MAC address, fooling host A into thinking the router is host B. Finally, host A sends its data to the router, which then happily forwards it along to the real destination.
Now, this isn't just some dusty old theoretical idea. It has some very practical uses, especially for connecting older, legacy networks that maybe weren't set up with proper subnetting. It's also used in some VPN setups to make a remote computer, say your laptop at home, seem like it's sitting right there on the office network. Pretty cool, right? So that's how a device finds the physical address of another machine. But what about the complete opposite problem? What happens when a device boots up for the very first time and doesn't even know its own logical identity on the network?
I mean, seriously, this is a device's very first question when it wakes up on a network. It's got this permanent, physical MAC address that's literally burned into its hardware, but it has absolutely no idea what its logical IP address is supposed to be. How in the world does it find out?
Well, the original answer was a protocol called Reverse ARP, or RARP. And you'll notice I said was. It is totally obsolete today, but trust me, understanding RARP is crucial because it shows us how we got to the modern networks we use now. Its one and only job was to answer a machine's first question. Who am I?
The process itself was actually really straightforward. A new machine would connect and just broadcast a message out to everyone saying, hey, my physical address is this. Can someone please tell me what my IP address is? A special RRAP server on the network would hear this, look up that MAC address in a pre-configured table, and send a reply directly back to the new machine with its assigned IP. Simple as that.
And this is where you can really see why RRP was so incredibly important back in its day. It was literally designed for devices like those early diskless workstations, computers that had no hard drive to store their own configuration. They had to ask the network for their identity every single time they booted up.
So we have these 2 protocols, right? Solving totally opposite problems. But this brings up a really interesting question. Why does Proxy ARP still exist in some niche cases, while RARP is completely gone, a relic of the past? The answer tells us a whole lot about what modern networks really demand.
And you can really see that contrast laid out right here. They are 2 sides of the exact same coin. Proxy ARP is this outward-facing question, I have your IP, where is your physical MAC address? RARP, on the other hand, is inward-facing. I have my physical MAC, what in the world is my logical IP address?
So why did ARP become obsolete? This quote right here, it just nails it. ARP was perfectly fine at its one very specific job. The problem was that one job just wasn't enough for networks as they started getting more and more complex.
And this table shows you exactly why RARP failed. It's the smoking gun. See, getting an IP address is just step 1. To actually do anything useful, a device needs its subnet mask, it needs a gateway to get to the internet, and it needs a DNS server to find websites.
As you can see, RARP only gave you the IP address, leaving this huge configuration gap.
So this need for way more information is what led directly to RARP's successors. First, we got BOOP, which started to add some of those missing pieces. And that eventually evolved into what every single one of us uses today, DHCP, the Dynamic Host Configuration Protocol, which basically delivers a device's entire network setup in one shot.
So when you think about it, the evolution from RARP all the way to DHCP shows how a single, simple need, just answering a device's first question, can drive decades of innovation. And it kind of leaves us with one final thought. What are the simple, fundamental questions we're asking today that are going to force our technology to evolve in ways we can't even imagine yet?